Okay, welcome back from lunch, everybody. So our next speaker will be Danai Deligeorgaki, talking about Canon permutation posets.
Perfect. Thanks everyone for coming, and thanks for the chance to speak here. I've been coming to ALCO for many years, actually before I even understood what the numbers in the password stand for. So I'm very happy that I finally understand that they count some Canon permutations, and I'm very excited to tell you more about it and our archive from a couple of years ago, our preprint on the archive with Matthias Beck. So this talk is going to be about permutations, posets, and polynomials. And let's start with the permutations. I'm going to talk about Canon permutations. Great. So these are multiset permutations. So I have a multiset with entries from 1 to n that repeat a certain number of times. And I want to consider multiset permutations there such that when I look at exactly the first occurrence of each number, I get a subsequence, permutation of Sn, that is the same as when I look at the second entries, the sequence formed by the second occurrences of entries, and the third and the fourth, and so on. So in the bottom of the page, you can see an example. Can you see my mouse, by the way, if I need something? Where I have numbers from 1 to 4 with multiplicity 3 each. And now the first occurrence subsequence is 1, 2, 3, 4. The brown part, I look at the second occurrences, the second time where 1, 2, 3, and 4 appear. Again, I get 1, 2, 3, 4, and the same for the third one. So this is an example of a Canon permutation. What about the permutation on the right side? Now I look at the first occurrence of 1, 2, 3, 4, and I get the permutation 2, 1, 3, 4. And then I look at the second occurrence and I get the permutation 2, 1, 4, 3 instead. So that's not a Canon permutation because they're different. Okay, so I want all of those to be the same. Great, so when the multiplicities are fixed equal to 2, then I can use a pattern avoidance condition to characterize these permutations. So you can see here the example where n is equal to 2. 4 of the permutations are Canon, whereas the permutations 1, 2, 2, 1 and 2, 1, 1, 2, they're not Canon because the two subsequences are different. And that condition characterizes Canon permutations even for larger n when the n is equal to 2. So that's why Sergi Elizalde introduced these permutations, and for the case m equals 2, he called them non-nesting because they avoid this nesting condition. But we're going to be working with larger n as well, so Canon permutations. Great, and we're going to care about a certain statistic on them, the descents. So we're going to call a Canon descent polynomial, or simply Canon polynomial, the descent generating polynomial for Canon permutations for a given n and m. And here by descent, I mean the positions in the permutation where the value drops that are sort of underlined in the example. So here I have an example for the case n is equal to 3 and m is equal to 2, where I have split them according to their underlying subsequence. And this gives me all Canon permutations. So then I can get out if I look at each of them and identify the descents, I can form their descent polynomial, and it's going to have coefficients 1, 7, 14, 7, 1. So there may be two questions that come to mind when you see this polynomial, right? The first one is the fact that it's palindromic. Is it always palindromic? That means that the coefficients read the same from left to right as from right to left. And the second is that this polynomial has a nice factorization into two other polynomials. Does anyone recognize these polynomials? So 1 plus 4x plus x squared and 1 plus 3x plus x squared. So this would be the Eulerian and Narayana polynomials. Does this hold in general? So, oh, someone wrote something, maybe a guess. Yes, exactly, Eulerian. Thanks. That holds in general. The Canon polynomial that I denote with a non-curly C versus the Canon set that I denote with a curly C. So the Canon polynomial factorizes as a product of an Eulerian polynomial which enumerates descents on regular permutations and a Narayana polynomial, or rather a generalization of it, which would enumerate which would enumerate peaks on dig paths. And in particular, these two polynomials are known to be palindromic. So our Canon polynomials are also palindromic, for example, for this reason. So this theorem was shown by Elizalde, by intricate bijective proof. So the goal of this talk is to view these permutations and these polynomials from the framework of PW partitions of Stanley, and in this way try to simplify the proofs and get more insights on the distributional properties of those polynomials. More reasons why they would be palindromic, or more insights on another property called gamma positivity. Great, so now let's move to posets for this purpose. So the idea is to interpret Canon permutations as linear extensions of certain posets. Now consider the poset that arises as a product of two chains, one with m elements that I denote with these brackets, and one with n elements. I take the product, I get this staircase poset, and then I want to label it so that across the vertical chains, the labels are fixed, and across diagonal chains, the labels follow a permutation of Sn. In this case, of the example 1, 3, 2. And in fact, if you prefer an injective labeling, there is a way to think of it through an injective labeling on the right, where so that the descents essentially do not change. But we're going to stick with this labeling with repetitions for now. So what are the linear extensions of this poset? What are all ways to order its elements so that the poset relations are respected? They are essentially going to be shuffles of 3 copies of the permutation 1, 3, 2 with each other, right? So that exactly captures the Canon condition, except that I require that this underlying subsequence is fixed. It's 1, 3, 2. So that's how the posets come in into these Canon permutations, and we can use this to understand the whole set of Canon permutations. So in particular, before I was thinking of the Canon permutations according to each of the subsequences they have. Now I can think of them as a collection coming from linear extensions of posets with, in this case, 6 different labelings, with n factorial different labelings coming from my permutations. And these 5 elements here that you see, the linear extensions, these are the Catalan numbers that I mentioned earlier. Great, so I hope that it's clear now that this gives me a way to visualize Canon permutations, and I want to think about, well, let me introduce the H-star polynomial of a poset, which is what I define to be essentially the descent-generating polynomial when I range over all linear extensions of my labeled poset. And then it's a theorem, actually, of Brändén that the H-star polynomial will, of any of these posets with different labelings from sigma, is going to be the same up to a shift by a power of x. So that's why the yellow part that you see, they're always the same, just multiplied with the power of x. And in fact, the exponent will be the number of descents of the permutation sigma that I used. So I think that's a quite cool theorem we came across when we were working on this. In particular, it means that, and it's a specialization, obviously, of a theorem of Brändén. And this implies by the definition of Canon permutations as summing the star polynomials, by the way to view them as unions of linear extensions for these posets with different labelings, it follows immediately that the Canon polynomial will factorize as the product of an Eulerian polynomial with the 8-star polynomial of this chain poset, which exactly is what I mentioned before, the generalization of the Narayana polynomials. Great. So far, this would recover the theorem. Now let me do a tiny generalization, one step forward, and say that I can also have a labeling on my vertical chain that I started with, let's say omega, and things are gonna still be nice. So I can have a labeling and I can construct in my new chain poset a labeling such that when I look at vertical chains, the relative order is respected, the same as in my labeling, in this case, 1, 3, 2, from top to bottom. And when I look at the diagonals, again, the relative order of the elements will be coming from the sigmas, from the permutation sigma. So 3, 4, 1, 2 in this case. So there's a way to do it, and things work nicely. And so immediately when I view these permutations from this setting, in this setting, I can say more things about them. And for example, I can say that the Canon polynomial analog, but this time allowing a different labeling omega, so which I denote here by just ranging over permutations and considering the sum of their 8-star corresponding polynomials. This is gonna again have a factorization as a product of an Eulerian polynomial with the 8-star polynomial of the chain poset times the power of x, which captures the descents of my omega labeling, meaning if I write down the linear extension of the poset, how many descents will I have of the poset, meaning the chain, the vertical chain. And in particular, for the identity labeling, this is exactly the theorem I was talking about before. Great. So one comment on palindromicity. Well, from this perspective, it's natural to see the palindromicity because it is known by work of Stanley that if a poset is graded, which means the maximal chains will have equal length, then the corresponding star polynomial will be palindromic, and hence immediately it follows by the theorem that, together with the fact that the Eulerian polynomials are palindromic, it follows that the Canon polynomials and their generalization that we talked about will be palindromic. But we also have an alternative realization, which is that I can take the chain poset that I had, and I can also take an anti-chain, and I can think of the elements of the anti-chain. I can make them to be covers of the maximal element of my product poset. And now this new poset, it has 8-star that is exactly my Canon polynomial for given n and n. This is what I call the Moose poset, because of our amazing puzzle-solving team. Great. So one last generalization of this theorem. So before we allowed labelings for the chain, the vertical chain, but in fact, we can also let it be any other poset R. So if I allow it to be any poset R, I can again define the Canon labeling in the same way and the Canon polynomial to be the descent polynomial when I think of products of polytopes, like in the example below. And I can still get a factorization theorem in the case when all maximal chains have exactly the same number of descents. So what I mean by that, for example, below, I have this V poset, and the maximal chains each have 1 descent because the chains are 3, by the labelings are 3, 1 and 3, 2, and each of those has exactly 1 descent. So my conditions are satisfied, and hence, I want to now think of Canon permutations, right? So I will, but this time generalized to posets, right? So I will look at each of these examples. So I take, for example, first the identity sigma, and it gives me that poset on the right, that product poset. I look at the linear extensions of that, then I will do it for another sigma, for example, 3 to 1, and so on. I will do it for all sigmas, and the resulting Canon polynomial will be, again, the product of an Eulerian polynomial with my poset times the power of x, or it can also be seen by this single poset that I talked about, the Moose poset construction. So yeah, we like that setting because it allows us to generalize very easily and think about these new permutations. But for now, I want to take a step back and talk more about the distributional properties of these posets, of these permutations. So hopefully it's somewhat clear so far. But if not, we're now going back to simpler. You can think about just the permutation states as the Canon permutations, not necessary to think about the posets. Great. So I want to talk about gamma positivity that, for example, Julia talked about yesterday, and it is a property of palindromic polynomials. So a palindromic polynomial is gamma positive if it has non-negative coefficients in the so-called gamma basis. For example, the Eulerian polynomials and the Narayana polynomials, they're known to be gamma positive. That means my Eulerian polynomial that was 1 plus 4x plus x squared here, it can be expressed in that basis, and the coefficients in this case turn out to be 1 and 2. And they're actually known to enumerate certain permutations in terms of peaks and avoiding double descents. And the same, the Narayana polynomials, they're also gamma positive. And in this expression, I get the coefficients 1 and 1. So I can combine the two and conclude that the Canon polynomials are gamma positive. And for this example, I can make the computation and I get the coefficients 1, 3, and 2. So that's always true. But what is not exactly known is what this 1, 3, and 2 count. How can I see this 1, 3, and 2 as Canon permutations? So that's what I'm going to talk about now. And to do that, I just need to think about a slight variation of descents. I don't know what's signless Stirling of this first kind, sorry. But this is signed permutations in a sense. So remember, let's denote by r hat my Moose poset from before. I take a permutation in there, a linear extension, and I want to give it color 0 if to the ith entry, if it comes from an even height of my poset. So you can see it in the examples how I label the heights with 0 and 1. And I'll give it color 1 if it comes from an odd height, just like in the example. So here I have the example 1, 3, 2, 5, and so on. And I bring in the corresponding heights. I also use, I also attach this a 0 in the beginning and the end. That's just for to help with descents. And then I wanna define descents for this signed permutation version, this colored permutation. I wanna think of a descent. So in the case where 2 consecutive entries have the same color, the same definition of descents apply. I want a larger number followed by a smaller number. For example, here I have 3 with color 1 followed by 2 with color 1. But when I have a change of color, I get a descent when I go from a larger color to a smaller color. For example, here I go from a 2 with color 1 to 5 with color 0, and that's a drop in terms of colors. So that's another descent. And that's all. Then I have 5 with color 0, followed by 4 with color 0, so it's going to be a descent, and so on. In particular, that permutation has exactly 4 descents. So I have a permutation that is a linear extension of this extended poset, and I'm gonna translate it into this pi prime that is gonna have also signs and think about descents there in this way that I defined. Great. So that takes us to our conclusion about what the gamma coefficients would be. So from this perspective of posets, of PW partitions, actually it follows again by Peter Brändén's work that we can find a gamma interpretation. He gave a gamma interpretation for posets just like the moose poset that we had. And if you translate this into Canon permutations, you can get out this corollary that says that the gamma coefficients of the Canon polynomial count linear extensions of this moose poset such that first, they have no double descents, meaning they have no two consecutive descents. And second, the ith coefficient the ith coefficient counts permutation with exactly I plus something descents. So this is an analog of the regular permutation case, in a sense. Let me quickly explain a little bit what this means. So in the example from before, we have the coefficients 1, 3, 2. And all that the theorem is saying is that now I have a way of realizing this 1, 3, and 2. And for example, if I look at the second example here, it has no double descents, no two consecutive descents, and it has exactly 2 descents in total, which is the minimum number of descents I can have given that I introduced these signs. So that permutation and its corresponding Canon permutations 1, 1, 2, 2, 3, 3, it's gonna contribute to the term 1 here in my coefficients. And similarly, I can find 3 permutations that contribute to 3 and 2 permutations for the last coefficient. Just by looking at the linear extensions of that moose poset. Great, so that's what this hopefully gives you a taste of what's happening here. And I have one last thing I want to talk about, and one last construction that essentially generalizes these Canon permutations. So now I want to consider Q to be a subposet of what I had before, but I'm going to remove some of the diagonal edges. So here the arrow means this is not there anymore, these edges. In general, remove some of the diagonal edges coming from the second chain, the n-element chain. Again, with the same machinery, I can think about the dissonant Canon polynomial that arises when I range over permutations and keep, this is a typo, and keep my labeling fixed. And why do I call them dissonant Canon polynomials? I do it because, well, in the case where I have the chain and the identity labeling, I can, well, they generalize Canon permutations, right? And not only do they generalize Canon permutations, so I have that I can obtain Canon permutations from that set when I remove no edges, but they also generalize regular multiset permutations. So this is probably more obvious from the example. So if I have a multiset, for example, here with elements from 1 to 3 and 2 copies of each, think about the linear extensions of this poset on the left. What will they be? They will have their first subsequence, of first occurrences is going to be 1, 2, 3, and the rest is just free to be whatever. So once I range over all possibilities for this first occurrence subsequence, I recover the set of all multiset permutations. So in that sense, because these arise from the Canon, from the chain product of chains poset by just removing some cover relations, like I said, along the diagonals this time. And so these are examples of dissonant Canon permutations. So the motivation for introducing this generalization is that we thought that Canon permutations and also the full multiset permutations, they have very nice distributional properties. They are palindromic and they have beautiful gamma descriptions, among other things. So we were wondering if something like that could extend to this family of classes of permutations in between. So which properties extend to that class? And we were able to prove that palindromicity does. So again, of course, we need to specialize in the case where the poset R that we multiplied with our chain, it's gonna have at most k descents in each of its maximal chains when realized as a linear extension. But anyway, the same results hold, and it turns out to be palindromic. But we used a different technique to show this sort of by bijection. And in particular, we couldn't get something like the moose poset analog here for this case. So we couldn't get to view this dissonant Canon polynomial as an 8-star polynomial of one single poset. That would be very nice if it was the case, but it's not, even though it is palindromic. And so we were not able to prove that it's gamma positive. But we conjectured it. We conjectured that these polynomials are gamma positive. We don't know how to solve it, or for sure if it's for sure true, but I invite you to try. And also, this is also a question that I have, is that I don't know other classes of multiset polynomials that are sort of a full degree like ours here, that are palindromic. So I'm wondering, well, is this class of dissonant Canon polynomials capturing all of them? Are there more of them? Yeah, what's the right way to look at them here? And lastly, one may wonder, since in this talk we have fixed a permutation sigma, and then we looked at all linear extensions of the poset with this fixed permutation there, what happens when you fix instead a linear extension and reigns over permutations? And so for this, I wanted to advertise our preprint with Chris Menon, where we look at this for the case where m is equal to 2. So in that case, linear extensions of this product of chains poset, they are just big paths. And we're able to tell some stuff about the descent polynomial there, but it's not known what happens for a larger m. And with that, I would like to thank you for your attention.
Questions for Danai? I can't really see if people are raising their hands because of all the clapping, so you should just jump in.
Yeah, I had a question. Very nice talk. Pretty results. Thank you. So descent seems to work really nicely on these types of permutations. Has anybody looked at there's tons of other statistics that you could use, major index, inversion, etc. Do these seem to be nicely distributed? Does anybody know?
I don't have a good answer.
It's something worth looking into then.
Yes.
I also have a question. So one of my favorite things to think about is the product of 3 chains. And I couldn't figure out whether your results have a nice sort of permutation interpretation in that context.
The product of 3 chains, meaning,
Yeah.
okay. So you can start with, can you start with the product of 2 chains and multiply it with the third chain? So that would be our poset R, for example. I don't know, yeah, like in this example, but I don't know about multiset interpretation. We sort of identify all these numbers from one poset, so yeah, I don't know, maybe it's something worth considering.
Can I ask a couple of silly questions? So I'm not sure if this is like closely related to your approach since you're working with this very concretely, but if you look at the general approach like related to gamma positivity using these like P and this other involution thing, does the family of posets you look at have like a nice like version of the like anti-chain like decomposition stuff. I recall seeing this like you have this smooth poset and you get this decomposition. I was wondering if that was related to that.
Which decomposition, sorry?
And into anti-chains.
Anti-chain decomposition.
Yeah. I mean, like it's. I guess what I mean is in a more general framework, you can reduce the positivity of like the kinds of posets you're looking at, where you're using this more general like get a positivity result into like a certain reducing the positivity of a certain class of posets. I was wondering if you like looked at the if
I
you
don't
you
think
said okay. I mean, I think you said you have a combinatorial interpretation of get vectors of certain things. So I was wondering if you also saw if the decompositions used to also look nicer here, but it's okay.
the
Thanks.
only thing that what you're saying reminds me of, but I'd like to learn more, is how Peter Brändén proves real rootedness of these things. And it starts by an anti-chain and adds things in and does a nice operation, which does not translate, does not work here.
Oh, okay. No, that's not what I was saying. I think what I was saying is that when he proved that like the real rootedness doesn't work, but then you do have gamma positivity for that class of things, he used like a certain reduction into like a sub collection of the posets that you're considering. And then I was wondering like, oh, if those sub collections look nice in your thing, but it's fine because I was just asking because you mentioned like a more general theory at some point in your slides.
Yeah, it's probably that I'm just not getting what you mean now, but okay.
It's okay. Sorry. No, you just mentioned some general theory. I was wondering if this specializes into a nice thing related to the structures you mentioned here. Thanks.
Mm.
Okay, let's thank Danai one more time.